So welcome to lecture 33 of MCS 472, a course on industrial computation and actually industrial mathematics. So we are looking today into the method of separation of variables to study the heat diffusion problem. So along the way, we will arrive at Fourier series. So in this course, we have encountered Fourier series multiple times. Here, actually, we encountered the original motivation for the development of Fourier series. So in some sense, this lecture comes towards the end of the course, but historically, Fourier series were actually developed to study problems regarding the diffusion of heat. So the method of separation of variables is very instructive to see the relationship between a partial differential equation and an ordinary differential equation. In particular, what the method will do, it will transform one partial differential equation into infinitely many. So this gives somehow an idea about the scope and the complexity of partial differential equations related to ordinary differential equations. Okay, so let's dive in. So what is our problem? So here is a very simple problem. Imagine a tube filled with hot water. So it could be just a cup, it could also be a tube. So the tube is insulated everywhere, but at the ends there is heat loss. So you could see this a little bit as you have a mug of hot tea. How long does it take till that mug of tea is actually cold? Here we formulate it a little bit in the more abstract. So the question is that if we look at this tube, we have insulated it everywhere, so no heat loss except at the ends. So the heat will disappear. The question is, what is the evolution of the temperature distribution? Can we model this somehow? Okay, so here is our mathematical model. Instead of a tube, we now have an interval from 0 to 1. Time goes on starting from 0. We have the heat diffusion equation. So how should you read this? So the change in temperature, so U, not U, but the letter U, is a function of two variables, x and t. So the change in time is proportional to the second derivative with respect to space. So at the bottom line, in normal English, what this says that the rate at which the temperature decreases is proportional to the concavity of the temperature distribution. So that's why the profile that we will consider, the profiles that we will end up with, will actually all be concave down. So one has a geometric interpretation for this heat diffusion equation. So this is a very simplified model, but it still applies to our tube. So we have an initial temperature which is everywhere 1. So we do this in a mathematical fashion without any units. At the boundary, we have temperature 0. So this models the heat loss from the ends. So at all times, it stays there cold. So you could think about a room where, or a house where the front door is open and the back door is open. And then you consider the line going from the front door to the back door and see how the heat dissipates. Okay, here is what I meant by concave down function. And this could be the initial profile of our heat distribution, other than taking 1. So this is a variation of our problem. I'm also flashing this sine function up to indicate what is about to come. We will actually describe the solution in terms of sine functions running at increasing frequency. So this is a sine function running between 0 and 1 that takes values also between 0 and 1. So in a way, this looks like a plausible temperature distribution at some point. Okay, so before we dive in, let us digest the problem a little bit, see if we can modify that a little bit. Here, throughout the lecture, we start with the cooling off process. The opposite process is, of course, warming up. We could consider heating a tube. So the tube is insulated, filled with cold water. But now actually heat is provided at the ends. So you could think about a hot water surface where the water actually circulates. So where the heat is actually, I think that's a little bit too complicated model, but so there is heat provided at one end. So this is a first warm-up exercise. Formulate the boundary conditions for this model. This will be flipping the zeros and the ones. The geometric interpretation is then that the rate of change in time is positive. So we will then deal with functions, profiles that are concave up, not concave down. But we can also say then that the rate at which the equation is still valid. So the rate at which then the temperature increases is proportional to the second derivative with respect to space, with respect to the concavity profile. Okay, so I hope everybody understands the problem now. If not, pause this video and scroll back. Let's now look into the mathematical solution. We will apply the method of separation of variables. We will decouple space from time. So we are mathematicians, we can do that. As persons, we often wished that we were at different locations at different times. But we can't do this, but we can imagine this. So this seems very unrealistic, but the main point also of this exercise is that you can see how partial differential equations relate to ordinary differential equations. So the three lines that are pop up in this content are actually giving the three kind of three different titles for what we are doing. We can see this as a method to model. We can see this as what it really means, we decouple. And then there is the relationship with the ordinary differential equations. I hope that will become clear. Okay, so how do we reduce to ordinary differential equations? So this method of separation of variables applies quite in general. So we always have space and time, where something is and when it is there. To simplify a problem, so thinking about time and space at the same time is complicated, assume that we can use different functions that only depend on space and functions that are only depend on time. Assume now that we can write a solution as a product of functions in one variable. We will see right next in the next slides that will give rise to two ordinary differential equations one in space, one in time. So that's then the application of the method applied. So we work with this assumption, and the assumption then implies that we can write a model solution, a proposed solution, as a product of two functions, one function capital T in time only, and a capital X in space only. So there's still a typo here, so this should be an X. Okay, so we will force this type of solution. So here, to be very pedantic, I use the capital U. This is a proposed solution. Just as our model is an idealized model, our solution here is a proposed solution. We are not claiming that is the solution of the partial differential equation. We will work with our assumptions. So we will now try to solve actually no longer the original problem. We solve a problem that makes assumptions. Okay, that having said, we actually see that our original partial equation, which is still here, which had a very nice clean explanation, now comes actually a lot longer. So it actually doesn't look like this is getting any simpler. So it's okay with taking the derivatives. So it's simply then taking the derivatives of the components in this product. But the original partial equation is now a longer equation. It's not clear that this has simplified anything. So, but don't give up. Let's continue. So now comes the key. So if we rewrite this a little bit, we write that the derivative in time at the left side equals something that is an x at the right side. But wait a second, didn't we just assume that these two were independent? So in some sense, if we look at this rewrite, it has not given us anything. But if you really want, or if you really believe the assumption that time and space are independently from each other, you can actually drive a wedge between the two equations. So we can wedge in something that is independent of both space and both time. So we started out with a function in two variables, the u, so not u, the letter u, but and now we actually say something. The assumption that we have a solution independent where time and space are independent, it actually then means that we can drive in something that is independent of time, independent of space. That means that it has to be a constant. So now you see the decoupling happening. If the time and space are independent from each other, we now actually have two equations that we can study separately. Good, so here it is, and now we are 12 slides in, almost 15 minutes into this lecture. I hope that now the main point comes in, what the separation of variable buys for us. Well, we have two ordinary differential equations, and ordinary differential equations we can study. What is actually most important already is that we see that when we look at the equation in time, it's a first order differential equation. It's a first order differential equation where the rate of change is proportional to the value of the function. And here we recognize the exponential equation. So this can often be seen also as the definition of the exponential function as the solution of a first order differential equation. So we have immediately a solution. And actually, the nice thing is that we can now do the first reality check. Is this actually now make sense? Well, it doesn't make sense we have a cooling off process. It doesn't make sense, the exponential growth. But we can say, hey, the lambda has to be negative. And this is written as the minus omega square. Seems fancy now to write this as an omega square, but this is a very convenient notation. In mathematics, choosing the right notation is solving half of the problem. Okay, so very good. After about 15 minutes work, we have a result. So this method of separation of variables is going somewhere. So we have indeed simplified the model. We can get the decaying exponentials in there. So because we are modeling a cooling off process. Okay, just as it was starting to get looking simpler, let's make this a little bit more complicated. So we have introduced operator notation last time, and you may actually have been, so I mentioned notation and choice of symbols. Well, the lambda, complicated Greek letter, the lambda is commonly used to define eigenvalue problems. So there is a connection with eigenvalue problems, but not the simple ones from linear algebra or whatever these were simpler ever. But we actually now look at functions. So the solutions that we are going to find are actually what is called they are called eigenfunctions. So we will have many eigenvalues, actually infinitely many eigenvalues, and infinitely many corresponding eigenfunctions. So there is an exercise. So the first exercise was a warm-up, and everybody should be able to do that. The second exercise is exactly the opposite. So this is also a math course. If you want to get a little bit more firmer footing in the more operator notation and the advanced math courses here, then please consider this exercise. So negative definite means negative eigenvalues, if that you may remember from a linear algebra course. And often a matrix with all its values, eigenvalues negative, is often taken as the definition of negative definite. It's a property that one can, in a rigorous linear algebra course, you would prove that. Here, the statement is generalized to work with eigenfunctions. So in some sense, this course does not well prepare for the rigorous mathematics, but the exercise is therefore also marked with a star in the textbook. And to prove this statement, follow the outline. Start with looking at the outline of the exercise in the textbook. Okay, the exercise itself goes more in depth and is somehow a tangent, a sidetrack, if you want to solve problems. But the notion of eigenfunctions is important, and eigenvalues. So in some sense, okay, so let's continue now. Where does the omega square came in? Why did we replace? So now we're no longer going to talk about lambda. So lambda is gone. Lambda is replaced by the negative omega square. And why is that now so useful? So omega, another Greek letter. But good that we talk about infinitely many problems, because we will see that omega comes up in the frequency of the periodic functions, the sines and the cosines. So when we studied differential equations, we had the most basic types were exponential growth. The other type of ordinary differential equations involved oscillations, vibrations, periodic functions. The sines and the cosines are actually designed for that. Of course, they have these very nice geometric definitions, but the sines and the cosines actually are solutions to this second order differential equation. As is explained here, you take the derivative twice and you see that the equation follows very naturally. Again, as one can define the exponential function as a solution to a first order differential equation, one can see the definition of cosine and sine functions as the natural solution set to the second order differential equation. Okay, so we have parameters coming in. This is a whole family of solutions. So I was mentioning eigenvalues, infinitely many solutions already. Here you see the families coming in, the A, the B, and the omega. All right. So what do we have? So we have solved two decoupled ordinary differential equations. Let them put together now. So we have three parameters, little a, little b, and the omega. And we also have the initial temperature in the first, the initial value for t, which actually at t equals 0, you could say is the initial amplitude. But we can pull in the t naught into the constant, so we reduce the number of constants to 3, capital A, capital B, and the omega. So what one sees now is that this is still a very rich model, so it's a simplification with the assumption of the separation of variables. But it is plausible because we have the exponential decay sitting in there, and we also have the fluctuations and the oscillations. It will turn out that that will suffice to capture any profile, any initial profile that we have of the heat diffusion. So, okay, so this is a simple form. But of course you can't use this because it's a nice symbolic solution. So in reality, people want to kind of make a plot. You cannot plot even this, so you can't really do anything with this. So let's try to find values for these constants, and we have the boundary conditions. So we have the initial conditions, but let's start with the boundary conditions. Okay. So we have two boundary conditions. Remember the original problem, we had our interval of the pipe that was not insulated at the end. So we lose heat at the end. So the outside temperature, if you like, outside the insulated tube is 0. So we have these two conditions now. The first condition actually leads to a simplification. We do not have to worry about the cosines anymore. So if we plug in x equals 0, the cosine at 0, multiples of 0 remain 0. The cosine at 0 is 1. Multiples of 0 is again 0. So the sine is always 0. So in this first condition at the left, we actually left of the interval, left of the pipe, we see that the constant a has to be 0. So we don't have to think about cosines anymore. Why does this is? Because exponentials, they decay very fast actually. But a property of an exponential is that it goes never 0. So therefore the capital A has to be 0. Very good. So you see this is a very nice standard problem. Everything works out fine. So this story has a happy ending. Okay, so let's now look at the boundaries, the other boundary, the right boundary. And now actually we see how the infinitely many solutions actually comes in. So we evaluate at 1, so we evaluate the sine omega. Now picking b equal to 0 would leave us with nothing, and the nothing is impossible because we have temperature at the very beginning. So our problem is not trivial. So we cannot set the capital B to 0. So the sine function has to vanish at omega, and we have infinitely many values for omega. So every multiple of pi, starting at 1, every multiple of pi will actually set this to 0. Now remember the eigenfunctions, well, here they are. So here we have now infinitely many solutions. So we used the right boundary condition, but actually we have infinitely many solutions. And this sign that kind of seems to be very confusing, because at this point in time, it seems that you just pick, and there are infinitely many solutions. Of course, we now have values for the amplitude, so we can make plots, but we still have this bn sitting in there. So actually, why did we have to do this? Well, it doesn't make sense to assume that in some sense the sine function is also decoupled from the b. So we can also allow for any value for n, we have a different b. So now we have also the solutions that are characterized actually by these coefficients, this bn. Okay, so this seems more like, well, your solution can be anything, but that's actually not realistic. I mean, how can this be? I mean, that the temperature distribution, well, this is not there should be a deterministic solution, so not just any possible function that can happen. Well, we can assemble everything. So it in some sense it actually gets worse, because the linearity of the derivatives, it also means that any linear combination of these basis functions is also a solution. So that actually makes that we have now a whole family of solutions, and there are infinitely many, and we have coefficients that are solutions in the basis of the sine functions that all have these decaying amplitudes. In a way, this starts to get quite complicated, but remember, we have not yet used the initial profile. So in a way, this new general form of the solution will prove to be quite flexible to accommodate any given initial profile of the heat distribution. So this model still allows for a lot of flexibility. And why is that? Well, here are the Fourier series. So in this course, we encountered Fourier many times. Also with the regression, we had the least square. So Fourier series approximate data in the least square sense. So let us recall how this works. So if we are imposing the initial condition, so we have at temperature, we have an insulated pipe of water where the temperature is the same, let's keep it at 1. That actually means that imposing that initial condition means that we have to compute the coefficients, the bn's, so that we have an approximation for 1. So we have now reduced our partial differential equation to a problem for representing data. So we are coming back to a problem that is quite familiar to us. Now, if you have never encountered Fourier series, then this is not trivial. Also, the orthogonality of the basis takes some use to. But let me phrase the problem here. Why is it going to work? Our sine functions running at different frequencies form an orthogonal basis with the inner product going from 0 to 1. So if you compute these inner products of different sine functions, then you will, it looks complicated, but you will see that the integrals, they actually are either 0 or 1/2, and you can actually don't have to compute them. You can tell by the frequencies. So sine functions running at different frequencies, they form an orthogonal basis. So in the approximation problem, we want to write 1 as an infinite sum of sine functions, and we can do that. So that's actually the origin why Fourier series were developed. So the coefficients of the Fourier series approximation to 1 will actually end up with explicit formula. So what we actually are going to compute, we're going to exploit the orthogonality of the basis of sine functions. So we consider the equality, so the condition on the coefficients, these bn's. We take the inner product of the left side with the sine function running at frequency m, and also at the right side. So we can pull in the inner product symbol, because the inner product is nothing else than the linear operator. It's the integral operator. And we exploit the orthogonality. So here you see that the coefficient, the only thing that remains here in this infinite sum, is the mth one, the m for the other basis function. So we actually want to do this with any m, but actually it turns out that the only m that survives is actually the m, and the only n that survives in this infinite sum is n equals m. Okay. That's the key property for the orthogonality. The other property that we explored in another lecture is that this will be the approximation in the least square sense. So with Fourier, with any orthogonal basis, as a fact, we not only reduce it to now computing integrals, something that we are very well aware, a problem that we know from calculus very well, but also numerical analysis that we can do very well. So our approximation problem is actually reduced to an integral problem. And since this is a nice, wonderful problem, it all has very nice explicit solutions. So we evaluate, so what we derived on the previous slide, we write down now using the formula, and you can, if you remember calculus, you remember this integral still, but if you please use SymPy if you have to do this. We have an explicit formula, so the cosine actually still comes up as the formal antiderivative. But if we evaluate this, then if you look at this very carefully, so the m is the index, so we're going to evaluate the cosine as multiples of pi. And actually only the odd multiples actually, so at an even multiple, at 2 pi, the cosine is 1, but here we have 1 minus 1. So only the odd multiples survive. In a way, you could have felt this a little bit if we are working at the interval 0, 1. At the interval 0, 1, our sine function will only make half a period. So we only have the concave down portion. We don't have the concave up portion. So in some sense, for a complete sine function, we should have considered multiples of 2 pi. So the fact that only odd multiples here survive can be also traced back to this. But it's okay to see this here in a purely computation. So the computations work out quite well. What this means is that we have an explicit formula. So here at the center of the bottom line, so this is the bottom line of the slide. For convenience, we go over to another index. So we are having k running from 0 to infinity, not from 1 to infinity, but from 0 to infinity. And since we are looking at 2k plus 1, we're considering 1, 3, 5, all the odd numbers, all the odd natural numbers. Okay, so there it is. We have the general solution. So that means we have a very nice closed form solution for the evolution of the temperature in time everywhere on the interval 0, 1. So what have we done? We assumed the separation of variables. The exponential decay came in. Very nice. The cosines dropped out with one of the boundary conditions. We had infinitely many eigenvalues when we used the right boundary condition. And imposing the initial profile led to the explicit calculation for all the coefficients in the Fourier series approximation. Okay, at this point in time, if we are interested in mathematics only, then this would be the end of the lecture. But of course, computationally, how good is this? So infinity is rather large number. We cannot afford in any computation to go there. And also, how fast does this model decay? So there are two convergence questions that we're going to ask now. How many terms are needed? So about this infinity. And we let t going from 0, we have this exponential decay term. So the amplitude starts at 1 at t equals 0, actually not at 1, so we have these coefficients here. But how fast does this actually now go to 0? So this is important if you were to go to a more, if you would change the initial temperature and the outside temperature, instead of working with 0 and 1 or 1 and 0, you would like to use more realistic temperature measures. You would like to bring in physical units. Okay. What if we use 10 terms? So here, this is at t equals 0. This is essentially the Fourier series approximation of the constant 1. Constant 1 with 0 at 0 and 0 at 1. So we have the interval 0, 1. And we see with 10 terms, we actually have a rather high deviation. So we have a 20% almost deviation. So it doesn't look actually very good. Let's double. Yeah, the deviation actually doesn't go down. Too bad. But you see that the approximation actually in the center, so now I'm at 40 terms, the approximation improves. The wobbles are still visible at 80 terms, but at 160 terms, well, the overshoot is actually still, I'm not going to get rid of that, but it will turn out that this will not be a complication. Because at these endpoints, the temperatures will actually quickly reduce. So it turns out that the Fourier series are actually very good for still a constant approximation. except at the endpoints. All right, so then that was the first question. Now this is the second question. So there's a Jupyter notebook that is posted at the time when the lecture happens. That is tomorrow in my time. So here I plotted for 160 terms in the sum. You see when t is, I had an exponential, so I was a logarithmic scale for time, 10 to the power minus, so actually this is expressed in milliseconds and microseconds. So this is at a very, very short time frame. And I only slowed down my time, so you can see in half a second, if this is measured in seconds, then in half a second the cooling off process here happens very quickly, whatever time units you want to use. Okay, so you can see the sine function coming in here, so it's not really at time, so I try to space it out a little bit, but you see that the sine functions are actually quite useful for providing a nice model for plausible heat profiles. So we started at 1. So one can try a bell-shaped profile. So a bell-shaped profile would be an exponential with centered at 1/2, and where the standard deviation is also 1/2. So you can look up what the formulas are for the probability distribution for a Gaussian. So this brings us back to the very first week of the course. Set up the model, and essentially you're going to compute the Fourier series of such a bell-shaped. And once you have these coefficients, you also have an evolution. So in a way, this describes a diffusion, a normal diffusion process. And this could be, and this should be, kind of a Gaussian that kind of gradually spreads out and degenerates into a flat line. Okay, so I have about 5 minutes left for a discussion on 2 topics for a proposal. So the textbook, so we worked through our first problem, a first standard problem in the textbook. The textbooks offers many problems, and our lectures do not have sufficient time to go in detail through all of them. Here is problem 3, which also discusses the diffusion problem, heat diffusion, but now on a ring. And the purpose of this project here is that you start with studying this solution, and once again, even if you're not interested in this particular project, please read the textbook. So studying another problem gives you kind of a broader range of the usefulness of this model. Also do the Fourier series computations. So these are not done so explicitly in the textbook, and certainly not the plots are being done. Essentially this is a reworking through the solution of the textbook and also the presentation in this lecture, but then on another problem variation. Okay, so we are interested in solving real-world problems. So here is a real-world problem. Assume that you have to procure the heating units for an expedition. So you have a whole troop of people who are going out on a camping trip. Imagine a school trip, and You will, everybody will camp out in the wilderness, and it can get cold at night. So you don't want uh, that any of your school children freeze out to death in the tents. So you will have to study which heaters are actually most appropriate. So of course you can trust any salesperson and walk into a joint where they sell these things, but you may want to do some study on the heat diffusion. So here, this is warming up. So it's very similar to our model, but now also with a twist, we consider the polar version. So you can still see this as as a polar, as a one-dimensional problem, but you want to study if the tents, all tents, suppose that we have now a circular base. So tents are typically not insulated at the end, but now there is a heat source in the middle. Um, for safety reasons, you don't want that people have to huddle too close to these heating units. So you would like to see that the temperature distribution is actually not a too fast decaying exponential. So towards the edges of the tent. Okay, so at the very edge, the temperature is the outside temperature, but you would like to have a smoothly decaying, not a very fast decaying exponential. So describe a model for this. What type of tent heaters are you using? Are there actually there are tent heaters out there? Um, describe somehow for which large tents what kind of tent heaters should you use. You can look at the specifications of these units, but the purpose is also to set up the model. Um, Okay, so I'm at the end. Timing worked out fine. So the method of separation of variables brought us to Fourier series. Fourier series are extremely important. We've encountered them too many times, or not too many times, appropriately many times in this course. They're a very important tool. As far as partial differential equations goes, one can appreciate hopefully a little bit the change in complexity, how one can look at the correlation of space and time, how that translates into infinitely many ordinary differential equations. So the purpose of this course, of these lectures, are that you find your way in the textbook. So we will not be able to cover everything in this chapter 11 in the textbook, but the hope is that the lectures provide you with sufficient background to find your way in the textbook, and most importantly, find your way into the problems that you will need to solve, either in industry, science, or government. Okay, thank you for watching this lecture.